Assalamualaikum warahmatullahi wabarakatuh, and good afternoon, everyone. And also maybe good morning if you are watching this session from Europe, where our today's distinguished speaker is. Today we are very fortunate to have the presence of Professor Mohammad Taherzadeh from University of Borås, Sweden. I hope I got that pronunciation right. So Professor Taher is an expert in fermentation technology, notably the anaerobic pathway using fungi. So hopefully he would share a little bit of his experience with his research team and also his worldwide collaborators with us today on how he progressed the development of knowledge in this very area. Yeah, he'll focus on the resource recovery part, which is very important now for us to also look on how we can close the loop, from the field to the laboratory to the processing stage. Then we got the waste and what to do with the waste after that, so that we can more or less get a maximization of resources available. Yeah. So maybe a little bit on the background on how we start, how we get to know each other. We were last time we're joining some scientific conferences together, notably in the Indian continent. Yeah. So we, together with other bioprocess scientists and also other researchers from around the globe, we were joining this. We were sharing some of our findings with like-minded researchers. Yeah. So without further ado, I would like to allow me to invite our distinguished Dean, Professor Rafiq, the Dean for the Faculty of Engineering, to introduce our speaker today. Thank you very much. Over to you, bro.
Thank you, Zainal. Assalamualaikum warahmatullahi wabarakatuh. Welcome everyone to our 112th UTM Engineering Distinguished Lecture Series. My name is Mohammad Rafiq and I am the Dean of Engineering, University Technology, Malaysia. Today it is my utmost pleasure to welcome Professor Mohammad Taherzadeh from University of Borås, Sweden. A bit about our distinguished speaker today. Mohammad Taherzadeh is a full professor in Bioprocess technology since 2004 at University of Borås, Sweden. He is also the head of Biotechnology Group and chairman of Research School at Swedish Centre for Resource Recovery. Professor Taherzadeh has PhD in Bioscience from Sweden and MSc and BSc in Chemical Engineering from Iran. He is developing processes to convert wastes and residuals to value-added products with focus on pretreatment and fermentation, where many of his results were industrialized by companies. He has published more than 300 publications in journals, 25 book chapters, and 5 books. He is also the editor-in-chief of Bioengineered journal. So that is a brief biography of our distinguished speaker today. Here now is Professor Mohammad Taherzadeh from University of Borås, Sweden, with a lecture entitled Biological Resource Recovery, Pretreatments, Anaerobic Digestion, and Fungi. Professor Mohammad Taherzadeh, over to you.
Thank you, Professor Rafiq, and thank you for the introduction and also the invitation. It is my honor to be in this session and your guest speaker, and I'm very happy to share what we are doing here, and hopefully it can lead to some kind of collaboration in the future. I will share my presentation, and I hope you can see that now. The topic that I'm gonna discuss is about this practically what we are doing as research here at our university, and it's about biological resource recovery. And I covered this 3 aspects: the pretreatment, anaerobic digestion, and also the work that we have on filamentous fungi. But we start with some introduction that I come from Sweden, which is located north of Europe, as you can see here, and the city of Borås, or Borås, that is located on southwest of the country. And our university is named also University of Borås. If you want to contact me and you see more information about me, is as you can see down of this PowerPoint, you can go to my website, which is taherzadeh.se, or here is my email and also this telephone, WhatsApp, and WeChat contact if you want to contact me in the future. But Sweden, as I guess many of you have not been in Sweden, we have in this picture that you see, it is in the summertime. It's something around 20 degrees that we have. It's perfect weather and condition. And we have about 10 million people, and yeah, it's more than half of the country is covered by forest, and we have around 9% lakes and river. So if you look at from the top by airplane, practically what you see is the trees and water that and lakes that you will see. And we have this language is Swedish, and we have something around 30 universities in the whole country. If you look at on the winter time, on the contrast, you see that we have a lot of snow in the winter, and it's usually white. Now at the moment, snow has disappeared in our part of the country in the south, and so it's we are heading to the spring. So we are expecting longer days and also more warmer also days. The university, which you see also at nowadays, it's look like this. We have a little snow, and then these are our buildings, University of Borås. At this university, we have 3 advanced research areas which are unique in the whole country. One of them is about textile, and then is the textile, we talk about the fashion and textile engineering and material and management. Another one is the library and information science that were also unique in the whole country. And the third one is our area, which is called the resource recovery, that I will explain more about this one. But the question is that actually why we need resource recovery, and why this topic is getting more and more interesting in the whole world. If you look at on this global population, as you see that it goes up. Nowadays we are heading to around 8 billion people, from about 2 billion that it was less than 100 years ago. And also we have a better welfare. So as you can see in this picture, that we used to, for example, use bike and biking, but now it's everybody wants to have driving. And one of the examples, you see that the number of the cars have been increased from 1970 to 2010, from 500 million to 1 billion cars that we have in the world, and it goes up almost every year. As the results, and a lot of similar factors, we see that this consumption of this fossil fuel is increasing. We talk about not only crude oil, as you see, the coal and also natural gas is increasing. And if you look at on the nature, if you put human as part of this natural recycling processes, we have, as a human, we are consuming our resources, that it could be this oil, water, gas, mineral, forest, and so on. And then we have, by our activity, we are convert these resources into some kind of waste in form of this gas, liquid, and solid, such as carbon dioxide, methane, and other things. And then we have recycling, which is happening in the nature using algae, fungi, bacteria, plants, insects, and so on, in different steps, and then converting back this waste into these resources again. That has been happening in millions of years, and it is still continuing. But in the last, if we say 100 or 200 years, we have increased this after the Industrial Revolution. The consumption of resources has been increased quite a lot, and also this production of this waste and has also been increased quite a lot. And as you can see here, that the nature is not in balance, and that is the problem actually. We see from one side, we are consuming more and more our resources, like we talk about depletion of oil or water or gas and so on. And on the other hand, we see the accumulation of this all this waste and gases, liquid and solids. If we just take one example, which is here that we just look at on this carbon dioxide, that it's quite known in the world. In the last 200 years, in year 1800, we had only the 0.03 billion tons of carbon dioxide production emission in the air. And if we see that today, it is more than 36 billion tons. And who is producing? It is almost everywhere in the world. We have this EU, United States, China, India, Middle East, Asia, Pacific, Africa, everywhere, that we are contributing to this production. And we see that the level of carbon dioxide is going up. You can see that continuously from this website that I put it here. Then it's going up practically between 2 to 3 ppm every year, regardless of all this international discussion and also debates that we have had. And if you compare these numbers, which is today something around 418 ppm, if you compare this number to the last 800,000 years, you see the level of carbon dioxide was between 200 and 300 ppm for such a long time. And there are some cycles, as you see in this picture, and every cycle represents one ice age. And each one, as you can see here, has taken something around 100,000 years. So if you say that what we are doing in 100,000 years, this amount of carbon dioxide has been decreased or increased by something around 100 or 50 ppm. But only in the last 50, 60 years, we have increased this one from less than 300 to more than 400, something around 150 ppm that we have increased in just less than 100. And that is the problem, actually. It's happening too fast, and the nature cannot adjust itself to all these changes. But if you look at on the other side, in addition to this accumulation, do we have enough raw material if you want to produce more of this energy, biofuels, biomaterial, and all these things that we are talking here? Just I'll show you a couple of pictures. Just if you look at on this municipal solid waste, only one material, we have something about 2.5 billion tons that we are producing every year. And that is actually, we are just dumping in the world. That is the major, I would say, tradition to dump it. And if you look at also industrial waste, we see also that's just two examples. If you consider your country, we talk about palm oil residuals, that we talk about something around 50 million tons per year. Or if you go to sugar cane and bagasse, we talk about 500 million tons. And that is just the two examples of thousands of examples that we can make. So then it means that what we need to do, actually, we have to make a new balance in the world. And in this way, that if we can accelerate conversion of this waste to these resources, and helping in this natural processes that is happening by all this microorganism and this bigger organism, then we can accelerate the whole things, and then the processes actually they can manage to reach with each other. So in this way, that we can make a new balance actually in the world by such a process. So, and that is the reason actually what we are doing in our center. In this center, resource recovery, that we are converting different type of waste and byproducts and residuals. It could be, you can say that municipal waste, agricultural waste, the forest, industry, and so on. We develop different technologies that it could be considered as material recycling, biological processes, chemical processes, thermal processes, and these are more an engineering aspect, but we have also some kind of social aspect, because if you talk about waste, you also talk about for example, you have to consider the behavior of people. So the question is that how to change behavior of people in general to make a better recycling and recovery of the material. So we consider all these residuals, convert it to different value-added products, and then give it back to the society. That is, in principle, what we are talking about. If you want to see more information about our center, then I put everything. We have the website. If you just write SCRR, which is this abbreviation of Swedish Centre for Resource Recovery, then you can come to this website that we have it here. And for our educational program, that we have this master program in resource recovery, which is 2 years master program. And it is 3 different specification, which is on industrial biotechnology and bioeconomy, having polymer technology, and also we have energy engineering. That's 3 areas that we have. And we have also this unique PhD program in resource recovery. So all the PhD students, they learn the whole process of this resource recovery and go deep into their specialization, that it could be about biotechnology, polymer, energy, or we say resource management, sustainable built environment, and consumer behavior. So they are practically connected to what we have in different research groups here. So I talk more about this. I come to just one of our research group that I'm the head of that, and it's called biotechnology. And here you see the people that we have. And we have some seniors, about 7, 8 seniors, and then some postdocs. At the moment, we have 4 postdocs in our lab. And we have something about 12, 13 PhD students that are working on this in this group, and something about, normally we have 4 or 5 PhD, something we call it visiting PhD student. Those who come here for usually between 6 months, 1 year, or maximum 2 years, come from different countries. We have from Indonesia, Poland, Brazil, Iran, Malaysia, Germany, Turkey, Nigeria, China, and so on. So in total, we have usually something about 30 people that we have in our group. And we have had a lot of also these people, and here you see the list of people who were graduated since 2010. So practically we have something in average, I would say around the 3 PhDs that we have had per year that have been graduated from our group. So what we are doing, and that is more come to a little bit more on the scientific part, we say that we have a vision that we say waste is a resource, but our knowledge is not enough to utilize it. If you cannot utilize it, then it's waste. If you can utilize it, it is not waste anymore. It's a resource, or it's a raw material to do something else with it. So what type of material that we talk? Here you see some pictures. It could be food waste. It could be, for example, chicken feather or agricultural residuals, manures, cow manure, chicken manures, horse manure. We have this company, for example, industrial waste like citrus waste, or a different type of textile, for example, waste, or whatever that practically something that nobody wants that is interesting, and some kind of interesting raw material for us. If you look at on these materials, what we see actually here, it is not a material. You see that it contains it has some sugars, starch, lignocelluloses, pectin, protein, fat, minerals, flavors, and so on. So actually, which all of them are good, but people don't use it. And just to throw it away, and the reason is that there are some challenges. And that is the challenge in that that's the first question for us to work with. If I take this lignocellulosic material that you just consider this plant cells, they are composed of this cell walls, and cell walls that usually we talk about this primary cell walls, secondary layers, and so on. And if you look at each of them, for example, within secondary cell walls, that is the thicker one, then you have this fibrils and microfibrils that are composed of this packed cellulose and then covered by hemicellulose and lignin. So cellulose is glucose, and hemicellulose is also different sugars like glucose, galactose, mannose, and xylose. And the lignin is phenolic compounds. So if you want to use this material, there are usually two problems or few problems that we talk, and that is why it is not used by the microorganisms for this degradation. And we talk about this lignin coverage and crystallinity. If you look at on the crystallinity, here you see that this package of this cellulose, just a cellulose in the middle, that there are different models that we have this, some of them, some molecules are in the core, some of them are the green one on the around and the blue one on the surface. And this package of the cellulose, then it's you have some kind of packages. We call it elementary fibrils, and they are connected, they are together, and then between them you have this free polymers that is called hemicellulose, and then also pectin that is normally yet to have. If you consider one of the material which has no pectin and no hemicellulose, I can mention this cotton. That's a very good example. That's used in our clothes, like jeans, for example, is very common. You have this material. There are some kind of crystalline, actually, material. No lignin, no hemicellulose, but very high crystallinity. And that is the problem, that this microorganism like this bacteria or fungi, those things, they have difficulty actually to eat it. If we take another example, just a similar type of problem, I can talk about these keratins that you can find it in the feathers, wool, and also your hairs. If you imagine that people who die and then put them in the grave, that one of the things which is decomposed last, it is the hairs. It stays quite a long time. And then why this material are quite resistant for degradation? It is because of this recalcitrant and this high crystallinity of this material. And that is because of this keratin structure that what we have. So it is a pure protein, but nothing, actually it's very difficult to degrade it. If I take another example, if you take this citrus waste, for example, it contains fructose as form of sugars, it contains glucose and galactose, arabinose, and xylose as form of hemicellulose, and also galacturonic acid as pectin. These are all good and then degradable material, and they are actually pretty good to be used for different processes. But we have some kind of this toxic material that is mainly composed of limonene, the things that you call it pill oil. It's around 90% limonene, so something around 0.5% limonene. And when this fruit is hanging on the tree, this limonene make it difficult to be degraded, actually, just to cover it against all this microbial and fungal attack. So if you want to use the citrus waste, then you have this difficulty because this kill all the microorganisms, limonene. So if I summarize this part, it means that we have a wide variety of this lignocelluloses. We have this recalcitrance effect. You have this problem of coverage by lignin, which is not easily degradable. You have accessible surface area for bacteria and cellulosome that are difficult, actually. You have the presence of toxic material like this limonene, and also some kind of indigestible material that are inside. So if you want to use such kind of materials for the processes, then we have to do the pretreatment. And this pretreatment, then there are different goals of the pretreatment that you can define. And this definition that it could be, for example, to make the release this cellulose and the structure, or remove this lignin and hemicellulose, or it could be recovery of this pure lignin, or reducing the crystallinity, or provide enough surface area for absorbing the enzymes to the polymers, or improving this disruption of the enzymes. Or you might think about this hydrolysis of hemicellulose or hydrolysis of cellulose, or removing of toxic material, or removing of indigestible material. Usually it's quite a hot topic that we have had in the last 20 years on this, doing this pretreatment. And the first question is that what is the goal of the pretreatment? Usually many of the students actually they forget about the goal of the pretreatment. But there are many different pretreatment methods, in total something around 40-50 methods that I can mention. You might think about the physical pretreatment. It could be in the category of different type of milling or irradiation, like a gamma ray, microwave, electron beam. Or it could be other pretreatment like hydrothermal, high pressure steaming, or this expansion, extrusion, pyrolysis, and so on. You might think about this chemical and physical-chemical pretreatment, and by different type of explosion, like steam explosion or addition of some kind of chemicals like ammonia become FX, or CO2 explosion or SO2 explosion. Or you can use some kind of chemicals like alkali or acids or different decomposing gases like chlorine dioxide, sulfur dioxide, nitrogen dioxide, and so on. Or oxidizing agent like hydrogen peroxide, oxygen in wet oxidation, and also the ozone. One of the examples that is nowadays more interesting is to use this organosol to separate, which in addition to different effect is also it can purify, it can create purified lignin. That is, so if you are interested to separate lignin in addition to the other effect of pretreatment like crystallinity, that is one thing that it is nowadays is combined with the other processes. Another one that could be interesting actually to consider is this biological pretreatment, which you don't need any chemicals or you don't need any harsh condition, but you can use, for example, this white-root fungi, or you can use this pure enzymes like lignin, peroxidase, or lactase, and so on, in order to degrade lignin. And then, or like this fungi, what they do, they are interested to consume this hemicellulose, but in order to reach hemicellulose, they have to degrade lignin. So they produce all these active enzymes to get rid of lignin and then produce to reach hemicellulose. That is also one way of this pretreatment. So, and I can talk a lot about this pretreatment, but let's move forward. So if what we can do with this material after the pretreatment, and that is what we are doing, we take the material and then in our group, we convert them into different material, this including hydrogen and volatile fatty acids and biogas fertilizer. So these are in form of this anaerobic digestion. Then we have also ethanol production by baker yeast and also fungi that we have worked a lot. And also we are converting them to this different feed and food like fish feed or human food, and also biopolymers. So let's have a quick look on this material. But these things that we are doing now, we are working in two different platforms. That one of them is more anaerobic digestion, another one is using fungi. This is what I try to explain now in just very quickly in detail. So if we look at this anaerobic digestion or this biogas production, which is very common in the world, we put different type of agricultural residuals like manure, slurry, bio-waste, or maybe energy crops, grasses, or so on. You put it in a big vessel, and then this closed vessel, so it should be anaerobic, there should be no air inside. And then you give them the time, usually we take about 1 month, and all this material are converted to something we call it biogas, which is mainly methane and also some a little bit of the carbon dioxide that is inside. So then we have this biogas is used for different application, like this cooking, lighting, heating, or cogeneration for production of electricity, or maybe purification by upgrading and then adding to the gas grid. And then the residuals that is left is usually used as a fertilizer if it's good, depending on the raw material. Fertilizer, or sometimes they just threw it away because of this not possible to use. So what is inside, actually what's happened inside this the process, we have this organic waste that first go through this hydrolysis step, and then they are converted to a smaller molecules, and like a sugar, fatty acids, amino acid, and so on. Then you have this acetogens. They convert them into different type of volatile fatty acids and hydrogen. You have like butyric, propionic, acetic, and so on. And then in the final step, you have this methanogens. They convert this mainly acetic acid and hydrogen that convert it to biogas. All these processes, they are all these microorganisms. They are working together, and this is what we have inside the process. So one of the things that we are working with this process is to understand the whole process and develop the process. So what we have done is we are working with the simulation, developing the processes, and also the, for example, we have simulated all this chemical reaction that happens inside the reactor. We talk about something around the 60 different reactions that are in the form of stoichiometry or equilibrium reactions that convert all different type of material to the product. We have developed a model which is now used almost everywhere in the world. So we made it open access so everybody can use it and make their own modification. And also we try to look at the whole process if we can convert them to different type of processes. So we have a lot of work on this simulation that we are using mainly this Aspen for such a kind of a program, and in a simpler case also we are using another program that is called SuperPro. Another aspect that we are developing in this anaerobic digestion is that we look at on this material of construction. And normally, we have stainless steel or concrete that are used for material construction, but we have developed something that is made of a textile, which is, as you can see in this picture, that we have, it's a textile, but it has properties and different coating in order to cover, to be suitable to be used as such kind of processes. And now it is used in, it is produced in the world, so we have tested, we have developed and tested together with the textile company, and then we have tested in different environments that it was in addition to Sweden. Then we had it in Indonesia, Vietnam, India, Brazil, those figures that you can see here. And now it is produced commercially, and they are installed in different countries in the world there. When we come to a little bit more scientific work and for this development of this anaerobic digestion, that one of the things that we are working on is this dry or wet digestion. So let's see what we talk about. If we look back on the digestion process, what we feed inside, normally we have a TS something around 10 to 12%. So it means that the feed that you give it to the process is something around 90% water and 10% solid material. Part of the solid material converted to the gas, and then the remaining of this solid material is usually about 3–4% in the digested or this slurry that remains at the end. This one is called the wet digestion or fermentation. That is a traditional use almost everywhere in the world. But here you have to add a lot of water, and also you get some kind of wastewater if you cannot use it as a slurry, and in many conditions it has some kind of challenges that you have. So then it comes to another process that we call it dry digestion. And what we do here is that we go up with this total solid. So in this process, we go up to this the TS of the inside. It is something around 30 to 50%. It means that the material, they all look like something, like this food waste that you have from your kitchen. And then a part of this material are converted to the gas, and the remaining TS, something around 5 to 17%, depends on the condition that you are using. So here, actually, you need less or practically no water to be added, and also you get much less or no slurry at the end, depends on the condition of the process that you have. So what we are doing in the lab, we are developing such kind of processes for the batch and also continuous. This one that you see on the top figure, that it is a textile reactor that we have developed for the batch process to be for a cheap, for example, to be suitable like villages or maybe a small household, something that they can use it for their own. And then the one in the bottom, there are the reactors that we have developed to be used as a continuous process for such kind of solid material or this dry digestion. And the reactor is look like this, that we feed in from this right in this figure. And then we have some kind of a screw inside that move the material slowly from right to left. And then we get the digested out. We have this retention time, something we can adjust it, let's say 30 days. And then we get the gas out from the top. So it was not so easy to design this one because we wanted to feed the material while we don't get the gas out. And such kind of things that we are challenged actually to make it in the beginning. And we have developed a lot of results of working with different type of material like this straw, manure, or this different type of waste that we have worked with. Then we come to another aspect that if the material are not or low biodegradable. For example, if you put this plastics or wood into such kind of processes, practically nothing happens into anaerobic digestion. But we have another process in parallel that it is thermochemical process. That you take such kind of material, it can go through gasification to produce syngas, that carbon monoxide and hydrogen and also carbon dioxide. And then you have, this is called this raw gas, and then you need to have this cleaning and then catalytic conversion to get methane, for example, and carbon dioxide. So these two processes could be in parallel, actually, that we have had. We say the first one, anaerobic digestion, is not effective, and the second one is pretty expensive. It works, but it is pretty expensive. So what we have done, actually, in this process, we say that in the first one, hydrolysis, which is not effective, and in the second process, we say that this catalytic conversion and cleaning, which is expensive. So if we take that one and then we remove these expensive parts and then connect them to each other, that we get a hybrid process. That we take this material, we do gasification, and then we take the syngas and then convert the syngas to the methane. And it creates a platform to convert this syngas to other type of product. And one of the things that we have developed here was to use this some kind of membrane reactors in order to produce, to increase this gas holdup and also mass transfer, which is that's a quite difficult one. So it comes to pure, I would say, chemical engineering, all these aspects to how to improve this mass transfer here. When we come to this other product and biogas, can we produce anything else if biogas is not interesting as a final product? So here, if you look at on the process again, and then we focus on this intermediate product, which is volatile fatty acids and hydrogen. So what we can do actually here is that we can produce them and then we can extract and then produce this volatile fatty acids that can be used for many different applications. You can use it, for example, to produce biofuel or bioplastics or as a mixed VFA or as a separate, actually, that's what you can do for many different applications. So it creates a new platform for this volatile fatty acids or VFA. So what we can do here is that in this process, we can boost the first part in order to produce as much as possible as volatile fatty acids or hydrogen or hydrogen. And we can also inhibit the second part, so they are not converted to methane. So we inhibit with methanogens, and in this way, we get this hydrogen out of the reactor as a gas, which comes automatically. And also, we should extract this volatile fatty acids, so they cannot be further converted to this methanogens to biogas. And that was one of the things that we have developed and was quite successful in our group, was to develop this membrane bioreactor that we use it internal and also external membrane that we have used to extract this volatile fatty acids from the system. And if I just show you one of the picture that how it works, here this is the picture of this membranes that are some kind of permeate channel, or we call it IPC. That when it works, you have this VFAs that pass through the pores of the membranes, and then we get this, we suck this VFA solution out, while no microorganisms, nothing else can come out. And it took several years for us to develop such a system that can work continuously without any stop for months. And that was one of the things that we have done. And then now we are developing this process for two different applications. Let's come to this one of this application actually that we are using also this VFA, and then it is a fungi. And then when we talk about fungi, usually that people think about this macrofungi, that like this picture that you see, that this was my favorite actually, that oyster mushroom. And then but actually the majority, the biomass, that it is in form of microfungi, that you have the picture on this left. So, and there are different applications actually. That's what you can see here is that if you look at this microfungi, that when they grow in water, it looks like the figure that you have on the left. And if you think about this solid state fermentation or the growth, it is one typical example. It is like a tempe that you have in Indonesia, or I guess you also might have it in Malaysia. That's a quite common food that you have. So it means that you grow the fungi in a solid form or in the liquid form and then convert it to different type of product. If you grow that in the liquid form, then in which way that it grow, that is actually, that's one of the difficulty, or one of the form. The desired form is like a ball. Here you see that it is, we call it pellet. And it's the pellets that if they grow well, that is what industry, they usually, they love if the fungi grow in this way. And it's like a ball, which is with the size something around 3-4 millimeters, as you can see in this pictures of how it look like. But one of the things that we have done, and it took several years for our work, how to develop this morphology of the fungi that they grow in a good way, and the nice pellets. And then in this picture, I show you different morphology, that they grow like a small pellet, the big pellets, or this like filaments that loose form, or they grow almost everywhere on the top, on the right, on the left, or they grow in the nice pellet in this on the right. So that is, it can go right, it can go wrong, and that is one of the difficulties that if someone starts to work with fungi that they will face. But what the fungi actually they do, and this is something that we have worked with them in since 1999, so it is 22 years that we are working with such fungi. They can convert different type of raw material. You can make a long list of this raw material. Then you can have this hydrolysis, and then this hydrolysis they can grow, and then you can have this when the fungi grow, they can grow themselves, and then you can use the biomass for different applications. Or they can produce these metabolites for different type of metabolite like ethanols or lactic acid and so on. or they produce a lot of enzymes, or they can also be used as a platform for immobilizing other microorganisms. But what we are working on is to develop some kind of fungal-based biorefinery. That has been our goal, and it is our goal. So in here, this picture, it is like a summarize what the way that what we are thinking. For example, that if you want to use this fungi to produce ethanol, just an example, you can take this, this fungi. They can grow on many different type of raw materials. Some of them you can put them directly. Some of them you can use them as like lignocellulose and so on after the pretreatment. And then you can get this different product like fungi or ethanol and such things. Let's have a quick look. Then we say that one question, what type of fungi that we should use? And here is the first question. The fungi that, what is the major product of this fungi? It could be like this ethanol that we talk. Or can they consume this sugars that you have, like pentoses, hexoses? Can they produce hydrolytic enzymes? So it means that you have less need of these enzymes. Or can they grow on different type of residual streams, different type of waste? And also another aspect that has been important for us, that the fungi should be edible actually. Not only grass, it should be edible. So we can use the fungal biomass as food or feed. And also other aspects like this morphology or the choice of the pretreatment and so on. So if you look at on this the process and this ethanol process, this is a typical ethanol process on this grain. They put grain here, you don't have any fungi, but let's see how this is a common process in the world. You take a grain, you do some kind of pretreatment, and then you add water. Then you use this, go through the hydrolysis step using, for example, glucoamylase and alpha amylase to convert a starch to sugar, and then you add yeast to do fermentation. After that, you go through the distillation, then you get ethanol as a product. And after that, you get this, the rest of the material, it's called a stillage. You centrifuge it to get a thin stillage. And then there's a cake, which is the solid material. It goes to dryer together with this thin stillage, which will go to evaporator. And then you get the syrup and then put it back as to dryer to produce animal feed. And typical size of such kind of process is something they produce around 200,000 tons per year ethanol. So it means practically they put 1 kilogram ethanol, 1 kilogram grain, then they put 1/3 kilogram of ethanol, 1/3 kilogram of this animal feed, and then 1/3 kilogram is converted to this carbon dioxide. Okay, and this animal feed DDGS is look like this one. So we wanted to have the focus on this edible fungi here. So we tried this different fungi. Or rhizopus, for example, from tofu and tempeh, they belong to Saccharomycetes. And then we tried this Monascus, Neospora, Fusarium, and Aspergillus from different foods that you have this red rice, oncom, corn, and also miso. And all of them are edible. And for this ethanol process, the one which actually gave the best result was this Neospora, that it produced more ethanol than the others. Okay, so how to integrate this process? So if I go back to this process again, this normal process, we can cultivate this, you see that you take this thin stillage and then you cultivate this fungal biomass, fungi to thin stillage. And then you separate this fungi, they grow themselves on thin stillage and then produce more biomass, and then you get this biomass and then dry it to get the fungal biomass. And also they produce ethanol, more ethanol. So in this way, that without adding anything else, you produce fungal biomass, and also you produce more ethanol without any extra material actually. Something that also you can do, you can take this lignocellulosic materials and then go through the pretreatment and hydrolysis and then add it to the fungal cultivation. So you produce also lignocellulosic material. And in this way, with a very, very low say investment, you can convert, you can integrate this lignocellulosic material or residual into this current ethanol processes that we have in the world. That is one of the big things that we are developing right now. Then it comes to the question that you get a lot of fungal biomass, what to do with it? One of the things that we have that we are developing is a fungi as a fish feed or fish meal, that we are cultivating different fish. So as you see, this is one of this picture that how it look like after this conversion of this material to the fish feed, and they are converted as a protein source for the fish feed. Another one that we are working, that we are converting the material to this food, so human food. Here you see this this meatballs, or you see the hamburger or the beef that we have. They are all converted from this fungi, actually. That's what we have. This is all fungi. And also you can, it's not only from this ethanol, so we are taking this fungi from different type of raw material or different waste material. Here we have in Europe, we have a lot of this bread waste. So we are cultivating the fungi on this bread residuals, like old breads that that we call it from yesterday that nobody buy them. Then, or we have this from this fish residual from the fish industry, or beer residuals, or we say this ice cream residuals, and a lot. So you name just the residual, and then we just look at it. If it contains carbohydrates, fat, and protein, we say that go ahead, that it will work. That is this typical picture that we have. And so when it comes to this product side, in addition to the fungal by itself, we're also working on this production of this pigments to produce different pigment. And this is one of the examples to produce this yellow or this red pigment here. And also, finally, I can also say that we are developing materials that take the fungi, do some kind of treatment, and then we can take, for example, the whole fungi and then convert it to this balls or this biofilms. Or we can separate the cell wall of the fungi and then convert them to super absorbents for hygienic products like baby diapers and so on. And at the moment, we have a project that is converting the cell wall to the textile material to this textile with some special application, like for example, like this surgery or this type of things. So in this way that I try to cover all this facts actually, or research what we are working here. And I try to go quickly so we can reach the material, and I can talk about all of them and in the time that I had. Thank you very much. So if there will be any question, that I will be happy to answer.
Okay, Taher, thank you very much for the nice and very timely presentation. I think we have around 6 minutes left, because we promised all our audience in this series that we're gonna try to finish this within 1 hour, yeah? So I have some question here. Do we have any questions? Maybe the secretary can share some questions if there's any from our FB audience. Okay, maybe while waiting for the questions to appear, I have one question here, Prof. This one is actually asked by one of my colleagues from a different school. Yeah, so like myself, I'm from the School of Chemical Engineering. So this one comes from the School of Electrical Engineering, actually. So he just want to know, is there any possibility to integrate an element of IoT, Internet of Things, in bioprocessing work? I mean, like when you're doing fermentation, you're doing a full-scale testing, what are the key elements that you're looking for, or you can suggest for the this element of Internet of Things to come in? Maybe you can suggest something, Prof. Over to you.
I haven't worked with it. I think that's definitely possible. But here, actually, that is something which is important. That we need to be a little bit more creative. That is something like the work that I mentioned about the textile reactors. that we worked with a company which was textile, which was completely different area. And then if you imagine this textile and biotechnology, they have practically nothing to do with each other. But when you put them together, and then we came to this point that something that we can well work together was developing this bioreactors from textile material. And I think if we, to be creative in this way, we can develop a lot of these interdisciplinary areas that could work. I think also that is possible to do that. But since we haven't worked with it, that it's something that we need more thinking about it.
Yeah. Because I think this happens also everywhere else. Now, most of the studies would be required to involve other disciplines as well. Yeah. So, okay, Prof, that is one question. So this question also comes from one of my colleagues from the chemistry department. Okay. So for after you've done your pretreatment, yeah, so you get different fractions. You get the hemicellulose fraction, the cellulose, and also lignin fractions. Yeah. So to get these fractions out, to concentrate it, normally people will use chemicals. Yeah. So is there any options then by directly using chemical, because chemicals tend to give side effects in terms of toxicity? Yeah. Maybe you can suggest something on that.
Yeah, actually, that's a quite important question for the pretreatments. That one of there are some chemicals, actually they are quite good for the pretreatment, like ionic liquid or those things, but we haven't worked with them. And the main reason is that there's side effect that it can give. If you develop any kind of process that you can reach almost 100% recycling of the chemical, then that process could be interesting. But if you cannot recycle part of it by any reasons, then it could be difficulty. Or you should consider some chemical that have less effect. Like, for example, if you are working with ethanol industry, maybe you can use ethanol by itself as this chemical. Then whatever that would be left, then it go to the process, and then you can get it back from this distillation column, for example. But if you take, for example, we have worked with a chemical like NMMO, that N-methyl morpholine oxide, and then we've done a lot of work with it. And we came into that point after a lot of work that when we've done this techno-economical analysis, that if you recycle 99%, it is not economically feasible, but we need 99.9% recycling. See? And I think this 99% could be possible to reach, but 99.9%, that is quite difficult. Yeah. And that is the problem that we have most of the chemicals that we have. Or if you come to this, for example, this acid pretreatment or acid processes, if you work, for example, you have to work with high temperature, with very low acid in order to remove the side effect of this sulfuric acid or other kind of acid that you are using. So that is quite important problem, but and that is why we have a wide range of these pretreatments, that many different chemicals, many different materials have been used, but there is no method that say that it works for us. Actually, that is the best. Still, we need quite a development, actually.
Yeah. Okay, Prof, can you see on your screen now one question from our audience, Mr. Steven? Can you see on your screen?
Yes.
Okay, the question is,
if we say that for this pretreatment for biogas production, what I say actually that something which we have to define first, what is this the goal of the pretreatment? That is, if you take this food waste or a sewage waste, sludge or manure, so we have three different type of challenges that you need three different type of pretreatment. So if you take, for example, this manure, you have this manure, it is the material which have been consumed inside this body of the cows, for example, and then what is remain that cannot be consumed, then it became manure. So you have, for example, some kind of lignin effect, or you have some kind of recalcitrance effect, that could be the question. Or if you take, for example, if you talk about food waste, depending on what type of food waste that you talk. This is the problem of this toxic material, like this citrus waste that I mentioned. So I cannot answer this one that we say we use this process. But we say in general, as less chemical as possible or as no chemical as process. So many of people, they use this thermal pretreatment or microwave pretreatment. They have been used, or in general, or something that the chemical that can be used by this by this anaerobic digestion, like for example, if you use acetic acid or ethanol or methanol, that can be used. So this type of processes that have been more common, but we cannot answer this question in just one, with one type.
Yeah. Okay, Prof. Thank you very much for the answer. So maybe if we have any more questions from our FB audience, maybe. Okay, not yet. Okay, Prof. Maybe we can have one last question. Yeah. I see. I was on your last slide. Maybe this question is coming from me. From your later slides, you mentioned about the edible fungi.
Mm-hmm.
Yeah. We are very happy that you highlighted about tempeh.
Yeah.
Because tempeh is kind of foods which are available throughout Malaysia. Yeah. Most people do eat tempeh. My question is not about tempeh, but about the natural pigment that you can obtain from fungi. Yeah. So is there any demonstration that this process have been brought up to maybe commercial scale, maybe just to see the feasibility of it?
No, that is, we have worked with two different fungi that they produce this pigments. That one of them was this Neospora that is used in oncom, that is also is Indonesian food. And another one was this Monascus that is used in red rice. But there was, the problem was that this economy actually, that if you just consider as this a pigment, separation of the pigment and use it as a pure pigment, it was too expensive compared to this synthetic pigment that are available in the market. That is so far that we have had a lot of discussion with industry that if they would be interested to use it. But what we are looking for now is that to take the fungi together with this pigment that make it interesting. For example, if you consider this fish like a salmon, people like this, we say this orange or red color that the salmon has, not bleached one. So, and because of that, they eat, they have to give pigment to the fish. So they get this nice color. That is what they do, especially, for example, in Norway.
Oh, really?
So, this is actually, this is, if you don't give them this pigment, then they come bleached. So the color of this flesh, which is like white, yeah. But so if you want to do that, then we say that you can give this fish feed, which contain this pigment. So it means that if you produce the fungi and then use the fungi, which is colored fungi, that could be more interesting.
I see.
This type of application that I think that could be closer to the, or like for example, this another one is egg. Some people prefer this more this yellow egg, which is more red color, yeah, not bleached yellow, yeah. Some people like that one. So in that case also you have to give the pigment to the egg, so they become a little bit nicer color. And so in this way that you have to look for such kind of pigments. Yeah, but we haven't. We say that the industry said that it is still too expensive. We have to find some kind of cheaper way, or some application that that's what we are thinking. That give it together with the fungi, with also as a bonus, the color. Yeah. But you might find some more interesting things in Malaysia.
Yeah. Okay, Prof. Yeah. Thank you very much for the answer. So maybe we can invite you again in the future. Maybe just to talk about this topic of pigment from fungi and its potential applications.
Sure. Yeah.
Yeah. Yeah. So I think we have now reached at 5:05 p.m. and I think in Sweden it's like 9:05 in the morning or 10.
Yeah, it is 10 o'clock in the morning.
Yeah. So With that, I think I would like, on my behalf, I would just like to thank you for your time today. I know you all have a very precious time over there. So thank you very much to spend some of your precious time with us today. And also look forward to have more sessions with you, and also maybe some engagements, maybe in the form of writing book chapters together, some review paper together with all our researchers in UTM. Yeah. With that, allow me to pass the session back again to our distinguished dean, Professor Rafi, to close the session. Thank you very much, Prof.
Thank you.
Thank you, Zainul, for chairing the session and for introducing Professor Mohammad Taherzadeh to me. And to our distinguished speaker, thank you so very much for accepting our invitation and for a great sharing session. So hopefully one day I will be in Sweden and meet you in person, because I've never been there before and it seems like a very nice country. So
Yes.
so hopefully we can meet one day, and of course you are more than welcome to come over here in UTM and in Malaysia. And to all our viewers worldwide, thank you for watching UTM Engineering Distinguished Lecture Series. Until next time, bye bye for now. Bye bye. Assalamualaikum.
Thank you very much. Thank you. Bye bye.